In Chapter 9, we're going to continue working with quadratic functions specifically. And in 9.1, we're going to work on graphing a simple kind of quadratic function in the form y equals ax squared plus c. Remember, the full standard form was y is equal to ax squared plus bx plus c. And so when you eliminate the bx, it creates a unique type of quadratic function. And they're pretty easy to graph, and they have some similarities that makes it easy to sort of get used to graphing and working into graphing the quadratic function. If you remember about parent functions, the parent function of a quadratic function, and a parent function is the function in the simplest form. This is, by the way, your vocabulary term, a parent function. Y is equal to x squared. This is the simplest quadratic function you can have, and it's called the parent function. So you can see the difference between the parent function and what we're working on is there's an added constant at the end, and there's a coefficient added on. And each of those will alter the parent function in a certain way. Okay, so our learning objectives for this section are to graph simple quadratic functions. Vocabulary is what is a quadratic function, and we've been talking about that for a while. The key is that the variable that we're looking for is being squared. That's what makes it a quadratic function. The graph of a quadratic function takes the shape of a parabola, and we'll show what that looks like in a little bit. I already discussed the parent quadratic function. And the vertex and the axis of symmetry are two key and very important parts of the graph of a quadratic function, and we'll go through those as we start graphing. A little more information. Right? This is stuff I've already reviewed. You might want to read this at your leisure. But this is what the graph of the parent function looks like. So this is a parabola. Right? When you have the graph of y is equal to x squared, its vertex is this point here. You'll notice that a quadratic function has one end that's close to vertical, and it comes back and it changes direction. It goes back to being vertical. And the point at which it changes is the highest or lowest point. In this case, because the parabola opens up, it's the lowest point. The quadratic function won't go below this point, the vertex, in this case. And that also means that the vertex has a close relationship to the range. Remember, the range is the collection of y values. You'll notice here there are no y values below the vertex. If the parabola opens down, and that happens in some cases, then there will be no y values above the vertex. But the vertex is always a boundary line for the range. Okay? A vertical line passing through the vertex exists, and it's called the axis of symmetry. And you can see that the left half of this parabola is a mirror image of the right half. In fact, if you look here at this height, 1, 2, 3, 4, if I move 2 points away from the axis of symmetry, I hit the graph, I move 2 to the right. That means if I move 2 to the left, I'll do the same. Down here, you'll see I move 1.5 to the right, 1.5 to the left is a point. 1 to the right here, 1 to the left. So items that have, or coordinates that have the same y value are the same distance from the axis of symmetry. Okay, and that helps us graph. It helps us cut down the time that it takes us to graph. So let's look at graphing. So I want to graph here this function. Now all of these functions in this particular form have the same vertex. They all have a vertex that's 0, 0. So what's great is it helps us, because normally in a full quadratic function, the first thing we have to do is locate the vertex. In these simple quadratic functions, we already know where it is. My vertex is at 0, 0. And anytime there's no middle term, remember ax squared plus bx plus c. When I say middle term, I'm talking about this term here. Anytime this middle term is not there, my vertex will be at 0, c. And in this case, C is equal to 0, so we're at 0, 0. Okay? So there's my vertex. And if I want to go ahead and find my graph, I know that there is an axis of symmetry that runs vertically through my vertex. So I'm putting this little blue line in. I know it's going to lay right on top of the y-axis to remind us that it's there. And what I can do now is I can look for points that are on one side of the vertex. I'm going to choose the right side. So if I pick 1 and 2 as inputs, I can plug them in. 1 squared is 1 times -3 is -3. 2 squared is 4 times -3 is -12. And you see that these values become large very quickly. That's a characteristic of the quadratic function. So you don't want to go too far from the vertex when you're graphing. So I'm going to plot these points, 1, 1, 2, 3, and 2, 12 would be way down here. And remembering that my graph is symmetrical, if I'm at this point, I'm at -3 and I'm 1 to the right of the vertex, that means there's a point 1 to the left of the vertex. And down here I'm at -12 and I'm 2 to the right of the vertex. That means also at -12 there's 1, 2 to the right of the vertex. And my graph comes through these points, turns around at the vertex, and goes out through those 2 points. And that's what my graph will look like. Okay, so in a nutshell, to graph a quadratic function, we first find the vertex and the axis of symmetry. Then we plot 2 points on the right side or the left side of the vertex, whichever you choose, and then match those points with their counterpoints on the other side of the axis of symmetry. And these 5 points will give us a pretty reasonable shape on our parabola. This shape is a parabola. Okay, let's take a look at another problem. Again, I've got no C, so C is equal to 0. I have my vertexes at 0, 0. And let's drop my vertex in there. That means my axis of symmetry, again, is coming right through here. And I'm going to choose values. You'll notice then it's going to be a little repetitive. I chose 1 and 2 in the last problem. I'm going to choose 1 and 2 on this problem. I'm really just choosing values for inputs that are right next to the vertex. Okay, so again, 1 squared is 1 times 3/8 is 3/8. And 2 squared is 4 times 3/8. Let's make sure we think about that. 3/8 times 4. 4 goes into 8 and leaves 2. 3/2. Okay, so at 1, this is going to be a little difficult for me to graph, but one thing I can do is I could expand my graph. So 1, 2, 3, 4. Let's make that 1. 1, 2, 3, 4. Let's make that 2. Right? 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. And then 1, 2, 3, 4. This one's going to open up because the leading coefficient is positive. I think I neglected to mention that. You'll notice this makes it open down. When the leading coefficient is negative, it opens down. When the leading coefficient is positive, it opens up. 1, 2, 3, 4. All right, so now we're graphing in quarters, and that's going to make this a little easier, right? So 3/8 is almost a half, right? There's a half right about here. So at 1, I would be at 3/8, a little less than a half. I'm sorry, this is 1 over here. And at 2, I'm at 3/2, so there's 1 1/2. Okay, so I was 1 to the right and at 3/8, I go 1 to the left and I'm at 3/8. And I'm at 2 to the right and I'm at 3/2, I go 2 to the left and I'm at 3/2. And now my parabola does this. So you'll notice that the shape of the parabola has changed quite a bit. two things have changed. This one opens down and it's very narrow. This one opens up and it's very wide. And the point of that, and what makes that happen, is the leading coefficient. So the leading coefficient impacts whether it opens up or down and how wide it is. So the larger the leading coefficient's absolute value, the narrower it will be, the more it looks like a rocket. If it's negative, it opens down. If it's positive, it opens up. And the smaller its absolute value, you know, so this is 3/8, so it's less than a half. The other one was 3. The more it's going to open up, it's going to widen out, and it's going to look more like an umbrella. Okay, so that's the impact of the leading coefficient. Okay, now we've got a C value added on here. Sorry, this should say Y. And the C value is going to do something to it as well. So notice we have a leading coefficient of 1. It's positive 1, so I know it's going to open up. And I'm going to put in my axis of symmetry. This still has a B value of 0. Right? Again, when I say B, I'm talking about this, ax squared plus bx plus c. So with the B value equal to 0, my vertex is going to be at 0, -4. Remember I said before it would be at, in this form, x squared plus c, your x-coordinate of the vertex is always 0. That's because B is 0. And we'll talk more about that as we look at the more complex forms. But then the y-coordinate will be the c value. So when we go ahead and graph this, again, you'll notice I'm going to choose 1 and 2. We're at 0, 1, 2, 3, 4. By the way, if I want to find the vertex, I can plug 0 in this case. If I plug the x-coordinate of the vertex in, I can show you that the y-coordinate, why the y-coordinate is the c value, and that's because this item, 0 squared, is 0, and we just are left with the c value. That's why we always know this is what's going to happen. Okay? When x is 1, 1 squared is 1, minus 4 is -3. And 2 squared is 4, 4 minus 4 is 0. Okay, so at 1, I'm at -3. And at 2, I'm at 0. So if 1 to the right, I'm at -3, 1 to the left, I'll be at -3. If I'm 2 to the right at 0, I'll be 2 to the left, I'll be at 0. And here's my graph. It comes in here, turns around and goes out. So you'll see, again, the leading coefficient is positive, so it opens up. And 1 is smaller than 3, so you'll see this is a little less narrow than the first example I gave you. Let's take a look at another one. Okay, again, we know that this is going to open up and it's going to be wider, more like an umbrella. I know my vertex is going to be at 0, -5, because my B is 0 and C is -5. So again, to sort of reinforce these ideas, the leading coefficient deals with whether it opens up or down and how narrow or wide it is. The B value, which in this case is 0, is related to the x-coordinate. It isn't the x-coordinate, but it has an impact on the x-coordinate. And the C value has an impact on the y-coordinate. Okay, it's not always that it is the y-coordinate, it has an impact on it. Okay, so my vertex is at 0, 1, 2, 3, 4, 5, -5. I'm again going to do 1 and 2 for inputs. 1 squared is 1, times 1/2 is 1/2, and 1/2 minus 5 is -4 and 1/2. 2 squared is 4, 4 times 1/2 is 2, 2 minus 5 is -3. So at 1, I'm at 4.5, and at 2, I'm at -3. Again, 1 to the right, I'm at -4.5, 1 to the left, -4.5. 2 to the right at -3, 2 to the left at -3. And then you see again, like we knew when we looked at the leading coefficient, this is a little more like an umbrella. Okay, so to review what goes on, when we're in the parent function, y is equal to ax squared, my vertex is at 0, 0. And when a is positive, it opens up. If a is greater than 1, it's going to be narrower. It's neutral, or what you might consider to be neutral or standard when a is equal to 1. And when a is between 0 and 1, it widens out and looks more like an umbrella. When the leading coefficient is negative, all those other things are true, but now it opens down. Okay, opens up, opens down. And when we add the c value, my graph is going to move up or down based on the c value. So c relocates the parabola by shifting it up and down. Okay, so c creates a vertical, the shift we call a translation. When the leading coefficient is negative and the graph flips over, we call that a reflection. So these are important words, right? So vertical translation is shifting it up and down. Reflection would be flipping it over an axis, in this case the x-axis. And here, when we're talking about the change of the shape, the widening and narrowing, that's called a vertical stretch. Okay, so in the previous chapter, we worked on describing the differences between a graph and its parent function. And I know that some of you had some difficulties with that. This is sort of the vocabulary that we would use to do that. Okay, vertical stretch, reflection, vertical translation. These describe how the graph is different from another graph. Okay, let's look at applying this to a real-world application. If I want to use a graph to determine things, so here's my graph down here. It's sort of a drawing that's laid onto this Cartesian plane. This is a cross-section of these parabolic solar collectors. And the graph of the function, here's the model, is over here. Okay, if we want to look at the graph and understand what's going on, let's try to figure out what's going on. So domain and range. So first the domain and the range. That's all they really want us to find out. So remember, the domain is about the x values. Okay, and you'll notice this graph doesn't continue on forever. These graphs did, with the little arrows on the end, but this, obviously this parabola doesn't continue on forever. It stops. So my x values are between here and here. Okay, so 1, 2, 3, 4, 5, and negative 5. So the domain is x is greater than or equal to negative 5, x is greater than or equal to negative 5 and less than or equal to 5. Okay, and when you think about the range, you can take a look at the y's, and the y's are between here and here. Okay, and if I wanted to find out that specific value, I would have to do something. I know that y has to be greater than or equal to 0, because it does hit 0. But then there's this value. How do I find that value? Well, I take this value of x, 5 or negative 5, and I plug it into the equation. So it's 0.09 times 5 squared is 0.09 times 25, and I'll whip out a calculator to do that. So I have 25 times 0.09 equals 2 1/4. Okay, 2.25. And that's finding the domain and range by reading the graph. Okay, you can see that all of my y values are contained between here and here, and all of my x values are contained between here and here. So domain is x values, range is y values, and that's how we figure that out.